So we are Tommi and Kari, and we are ready to deliver our talk on LiquidAI, or orchestrating cloud edge continuum with the isomorphic software. Well, like Cesar said, the baseline of this, or the basics of this work were laid in the 10 years ago in the context of liquid software. But since then, things have changed, and then also the domain where we are talking about liquid software has changed a lot. Okay. Originally, when we were introducing the concept of liquid software, for us, that meant that the UI would follow the user. So user experience roaming was also another name that was used at that point. But since then, a lot of things have happened. First of all, these big tech companies have started to implement the same kind of features. Apple has this: start watching a video from one Apple computer and continue with your iPhone or the likes, and so on. And then we also realized that even if it is annoying to have the same software or to install software to 3 different devices or 4 different devices, it's still a relatively small number of computers to worry about. And we are, well, at that point, we were thinking that maybe it is not a matter of introducing a new programming paradigm for 4 computers, but for millions of computers. So many that we can't even name them all. So basically, instead of computers as pets, we are talking about computers as cattle. There are so many computers that we don't even want to think about it, and yet somehow the correct program should be there, or the correct application should be in place when it is running. And this led us to turn to IoT with the liquid concept. You want to add something, or do we do? I don't know.
Let's go by the slides.
Yeah. And I guess that since we are software engineers, it seems to us that there's a big bunch of things that get all the hype: mashups, big data, now machine learning, AI, IoT, 5G, 6G, and all that. And somewhere under the surface, they are all just pieces of software, which means that whatever fancy technology comes in, you need the software building blocks to make it happen.
And this maybe to add to that is that we are talking about AI in here, but we are not developing any new machine learning algorithms or anything like that. It's just building up the software infrastructure where some of the components happen to be these mysterious machine learning components. And we have to understand special characteristics of those, but still we are not machine learning experts. So bear that in mind when we are talking about AI. We are talking about that from the software engineering point of view. This big part of the iceberg.
Yeah, and fundamentally, if you think about the direction where we're heading, is that whatever device you have, chances are that you can write code to it. And this is everywhere. I'm not sure even if the socket here is now smart and has some kind of an application in it, but boy, this building has a lot of computers. And boy, they are probably all interconnected somehow, and you could make them work together to do gazillion things. And this term programmable world, it emerged early 2010s, and it literally means that we are entering an era where whatever you have in your environment or surroundings is actually a computer that is hidden. And somebody has written code for it, and probably somebody is monitoring what it's doing and how it is behaving and all that. All right, so how do we get there? What is the road to this mystical programmable world? How many of you have been working with IoT stuff? Yeah, I would guess pretty much everyone. So you know that if you look from far enough, the systems look very, very similar. You have devices that are actually dealing with the environment. You have some sort of gateways that connect the actuators to the cloud. You have the cloud that does a bunch of stuff, and then you have the applications where you have the user front end. And if you start to build such a system, you quickly notice that for programming devices, you must understand really low-level stuff. Maybe you still have an operating system, but pretty small one. Gateways, well, they are today mainly headless Android variants and the likes. Cloud, yet another thingy, open source projects and so on. And finally, the applications where you use the web stuff or mobile stuff for the UI. Well, and this is all working pretty fine as we speak. We have been able to do these kinds of systems for dozens of years. What is actually happening is that we are really getting a big pile of possible software stacks for all of these things. So depending where you start from, you might have an operating system or maybe not. You might have a runtime operating system, or maybe it is a variant of Linux without any runtime support. There are even devices where you only have the language runtime, which you can make pretty small, but still programmable. You can have the full Linux. You can even have the full Android. And then there are a bunch of devices that are even beyond that, building on Node type of stuff. And then we are not talking about very small devices at all, but the big ones. And I think we are gradually more and more in the era where also this container operating system is becoming commonplace, simply because the hardware capabilities have been increasing so much. Should we skip this? Because
yeah, maybe return back to that
if necessary. It is just that all these stacks are there for a reason, and the use cases are completely different. But what is important here to grasp is that there are four corners in the IoT development. So we already mentioned that the IoT devices need certain technologies for implementation. Same thing with gateway, same thing with the cloud, and same thing with the end user applications. And it is actually difficult to find developers who can master all this. I mean, sure, you can adapt, and sure, you can do nice things, but it takes time. And in fact, if you want to build this, you need to understand the whole enchilada of modern software development, and you need to have all the possible skills. While we speak, this is becoming even more complex because now the requirement seems to be that every software developer should be able to throw in some machine learning components or some data analytics and whatnot. Then comes the idea that let's make it robust and replicate some of the things and so. And really, and this is almost like Hitchhiker's Guide to Galaxy to me, that whenever there is someone who masters all this, the assumption is that it is even something more complex and ludicrous that the expectation becomes. All right. What if we then do what the textbook software engineering approaches say? Let's make it more flexible and see if we can share something. And all this, let's make things more flexible, is based on a fundamental shift in computing power. So instead of calculating every possible bit, there are devices that are quite cheap, and you can do really a lot of stuff with those. So I spent some time with Mozilla. I mean, for me, an ION opener was I was having a lunch with this ex-Mozilla guy who had gone to work in a Silicon Valley startup doing baby monitors that are hidden inside a bear. I mean, not a real bear, but the baby bear. And we were having lunch, and he was describing what they are doing. And then I started asking. I mean, they said that yes, the sensor goes inside the baby bear, and then we put the stuff in the cloud and are able to do. I mean, on one hand, baby monitoring, yes, but at the same time, we are collecting data to predict this. What is kätkytkuolema? The type of death that the small babies can have when they have some breathing problems. So that they would learn enough to predict also that, at which point they were then thinking that if we can sell this with the CE marking, that is going to make everybody hellishly rich. Or at least that was the story by then. It's 7-6 years ago. And then I started asking technical questions and what kind of sensors you use? Have you got prototypes already? And the guy said that no, we don't use sensors. And I was, how do you make a baby monitor without a sensor? And he said that we use Qualcomm chips. They come with Android, are immediately available, much cheaper than whatever we would be able to print for 10,000 or even 50,000 teddy bears. So we decided to go for them. And then it hit me that this is happening everywhere, sooner or later. We go what is available, and what is available is having really a lot of computational capacities in comparison to the old days when you have to count every bit. Even I have had a programming job for a satellite, and it had in the beginning 128 bytes of RAM, and the whole maintenance or the whole operating system should fit there. And we don't need to do that anymore. Rather, we need techniques where we benefit from this added performance. And not like in the desktops where we mostly waste it for unnecessary animations and other stuff.
Yeah. Yes, about to just say this words of programming dynamically. So it's the one part of this new ways of deployment is that in addition to manufacturing and installing the software with the baseware at the factory, there are all huge possibilities to add new functionalities there. And then one driver that has been opening the eyes in some companies is now this regulations like Cybersecurity Act or European Union that actually forces that the software needs to be updatable if there's some security problem found on a connected device. So that means that in addition to be programmable, in addition to be powerful enough to run all kind of fancy things, one of our pre-assumption is that the software needs to be dynamically updated and changed in sometimes even wide ways.
Okay, so I already mentioned that let's make things more flexible. And couple of years ago, I don't remember where we met. We were talking about this isomorphism in software with Cesare, and then even eventually did a paper where the idea was that what if we try to add a harmonizing layer to the IoT picture? So instead of 4 corners, like in the picture there, you would have a unifying layer that allows one to run the same software in any of the devices. So more conventional term isomorphic is used in connection with the web. And there it usually means that you run JavaScript both in the browser and on the server side. But here we are thinking about the type of isomorphism which would allow you to run the same code in just about any device, not just browser itself or the server. So basically like the old Java slogan, write once, run everywhere, but this time run right. But by the way, Java 1 is happening again about the time we are speaking now.
Yeah, should be this week.
Yeah. Okay, I already mentioned JavaScript. So one way to do this isomorphic thingy would be that you use the same language everywhere, given that the language is dynamic, so that you would interpret it on the fly, and hence by putting an interpreter to every device, you can do whatever you like in every device with the same software, assuming that you have the APIs and resources and the stuff like that. And the other thing is that you put there a runtime that is able to run whatever programming language you have in your mind. And this is the approach that we have been following lately. The original thingy that we did with the Liquid software was more based on the language paradigm, where JavaScript was really used to implement just about everything. And here by isomorphic software, we mean that the software can really flow, or the same software can live in the different types of devices with this unifying layer that we have introduced. And when going towards the Liquid software, we are pushing the boundaries a bit more. This is taken on the trip when we were giving the Liquid software workshop at in here, not in this building, but the old campus. What, 2016?
2016, yeah.
And this was what we found on the trip. But this might not be a typical Swiss multi-device experience anymore. This is the old vision of this Liquid software. Is if you have ever watched Star Trek or other sci-fi stuff, you never hear them saying that my facial app is another computer and it's upstairs, or that I have lost all my files, or why can't I just make things happen? And this has led to the concept of Liquid software, where the software just flows from one computer into another, where it is best located for whatever mission for the software has been given. For the user interface, it is of course the one that the user is looking at, but for an IoT network, that's a combination of gazillion parameters that can be defined. So earlier this week, we went up north in Finland to Oulu to think about how these features could help in intruder detection or tampering detection in IoT networks by one of the security companies that operates there. But really, there's so many use cases where this could be helpful that I don't want to lock your imagination. You can think of it like a puzzle where you can first put the pieces together and then glue the picture on top of it with the liquid stuff that goes to the right places. Yeah, the original vision also had a demo video where one of the glass manufacturing companies had a vision that one day UI will be part of the glass that they make, so that you can not project, but put really the wiring that is used for UI inside the glass, making every window a computer screen if necessary. And this is the type of thing that led us to consider the IoT use case. Yeah, I don't know how to explain this.
Maybe
today is the first day that I saw it.
Yes, it happens to be my pictures. We actually reused both slides from both of us and some of our colleagues and collecting these things. So this is actually more about the liquidity in terms of edge and IoT. So the previous one was still on the user experience, the screen experience moving. But now we actually having this idea that we have an interconnected world of having cloud stuff. We have network devices and a network infrastructure. We have devices that are closer to humans somewhere in the buildings or wherever they are. And everything is programmable. These colors are originally just to highlight that, remember, and for a certain audience, that in addition to network infrastructure, it's also somewhere else, and you have to take that into account as well. You might imagine who might be the people who think that software is only in network infrastructure. And then there is also the same thing, that actually the software can flow and move. And you could, for instance, imagine that you have some IoT devices that are following you. Think about like a Cesare who's moving here in many places. You have your own application for this device. And wherever you are, it comes here, remembers what you have been changing and so on. So that could be the example of really a system to move, or it could be room temperature that is following your preferences if the code is moving around. And then we have done some practical experiments with WebAssembly. So as Tommi said, we started these things with JavaScript. We had Node.js runtime in all devices that we used in our experiments. But then came this WebAssembly that promises some additional benefits in terms of robustness, safety, supporting multiple programming languages, etc. And it's supposed to be fast, safe, and portable. And that's something that we have tried to investigate in our latest research. Neonative performance.
So how many of you, by the way, know?
Oh, yes.
Already?
That's, by the way, good point. So it's originally actually a technology for browsers to contain faster plugins that you can do with JavaScript. And the modern browsers actually have support for this WASM runtimes that you can run more like almost like binaries in the browser. And the idea is that you can use multiple different programming languages to compile this WASM runtime. Did somebody remember Java applets? But anyway, and there is also been brands, and I think Tommi brought that idea from Mozilla, and one of our common friends has been working in Mozilla on that thing, that how to use the same runtime on IoT cases, and we continued from that area. And it's language, hardware, and platform independent. There's open standard based. There's a W3C standard in some of these parts, and it's compact, modular, etc. It looked like, okay, this is the way to go. And in this project, we decided to use that for most of the part. If somebody just wants to know, so the most of programming we have been exploring the Rust programming language, just because at least in our university at the same time, those guys who are closer to hardware are so keen on that due to these safety reasons what they have. And now this is the outside of the browser thing, and it accesses some of the operating system functionalities, and there are developments of this fuzzy interface for the native stuff. Of course, we have to also be honest, we have been somewhat disappointed on how well this fuzzy standardization and ecosystem has been developing, and but still we have been working on that, and there are some security models and security features, and if some of you ever went to see the Java virtual machines that have these bytecode verifiers, etc., there are somewhat similar properties in WASM too.
That said, there's also a downside to this open standards, and that is that there are many competing implementations, and they implement a different subset of standard features, which make it sometimes difficult to decide that which virtual machine I can actually use for my use case.
And then but this is anyways open. It's open source. There's at least attempt to standardize it, and there are maintained tool sets for Rust and C and C++ and maybe some others I don't now remember, but it's there anyway, existing thing.
And this wasn't time is mentioned because that's the reference implementation. Tries to follow the standards.
Yeah. You know this slide better than I do, so.
Okay. Right. Okay. With this infrastructure, we then went on and decided to experiment a bit how isomorphic things can be. And then we did a small prototype where the virtual machine was extended with capabilities of loading WASM modules dynamically on the need basis. And once you did that, the new module would be instantly put to life. So as a proof of concept demonstrator, we implemented a Marvin, the bot from this Hitchhiker's Guide to Galaxy, that would have a personality module we could change on the fly. And depending on which mood was being loaded, it would, well, give a very sarcastic or pessimistic or happy or high, being high type of answers to just about every question. And unfortunately, we were never, well, mainly because I left from Helsinki and joined Jyväskylä, we didn't build this far enough to make it really a platform. So it was like a demonstrator that, yes, we can do the liquid stuff with the WebAssembly and make it run. And of course, the demos were cool, but they are now at the Helsinki University machines and not on my computer. Probably some stuff exists in YouTube. I can try to dig if someone's interested. Okay, now if you look at the modern day architectures of this cloud web continuum, cloud edge continuum that we promised, our vision is that every computer in this continuum knows WASM. And if they know WASM, they are able to run whatever modules we give to them, given that the APIs are correct. And in our wildest dreams, we are also thinking about the roaming on the fly. So changing the location of one computer from one module to another computer so that it doesn't even stop executing. But at the moment, we are not there yet. So instead, the things work so that there is a central component in our system that first looks at the capabilities of different devices that are included in the system and then makes a WASM module allocation to the computers that have been registered to the IoT network. So this is how far we are at the moment. We have this up and running. Ture will show a demo hopefully tomorrow morning, not to put any pressure, but the wink wink. And yeah, and at this point, of course, the question arises that how well do these WASM modules then perform in comparison to native stuff?
Yes, I can show that part of the thing. So I had one student who actually then took and did the measurements and on really comparing with three different programming languages, and then comparing it, the binary speed on that device, that was Raspberry 3 or 4, I don't remember now. And then WASM time and WASM, two different WASM runtimes. They all, and the research contain a couple of few micro benchmarks on different devices. And the bottom line there is that is a little bit less than 2 times, a bit depending on the programming language, that what the difference is. So the idea was to have as equal as possible the software, trying to filter all kind of over optimization of the compiler, etc. So, but it anyway gave us some perception that what does it mean when they're advertising that near native performance. There's still a gap, but not a radical gap. Then another study we did was actually to think that we compared these different WASM runtimes. As Tommi said, there are different implementations, and there are also the differences in the technology. So some of these runtimes are based on interpreter. Some of them have just-in-time compiler. Some of them have this ahead-of-time compiler type of approach. So it means that when the WASM module arrives to the system, to the target device, it does the local compilation to the local machine instruction set and runs it there. And then the score is there to compare to native performance.
I didn't actually know that WASM Edge was so good.
You have seen this. Pay attention to details.
Yeah.
And then there's another project of colleague of mine. They were interested on really even smaller devices. And there, what happens is, I'm not going to all these details of these numbers. If somebody gets interested, we can share this. Is that if your device cannot handle the compilation time, typically it is that the compilation takes memory, and you can't do that. If you can't do that, the performance starts to suck. And that's been there. After saying that, I was on our way here. I was reading an interesting article of some researcher actually made a new implementation of the compiler that can run on small memory. It was really kind of stream-based thing that it did not even try to have everything in the memory at the same time, and had some clever design decisions that we were able to actually achieve this near real-time performance, even smaller microcontrollers. And then then the next thing that we have been looking at is that, okay, we have these low resource devices that can you really run the machine learning models there? Or under what circumstances, what are the constraints of running them there? And another question has been that how well these portable ML models work. This ONGs, for instance, as an example. And in general, that what is the picture of running these ML models in this liquid context? And remind now, in our current project, the idea is that machine learning model or traditional computation, we should be able to treat them equally. They can also move and be installed to new devices. And how to do that?
And also many of the IoT use cases are actually building on these ML models. So you can filter out stuff that is no longer needed for more abstract levels, or you can make cascade the results or whatsoever. And there the machine learning models play a really, really big role
and now,
in processing.
And Tommi was mentioning this extreme dream of codes even moving around. And we assume that the machine learning models are arriving to a device, execute the inferences for some time, and then maybe move over. And that's why in our benchmarking, we actually think that we are calling this initialization and load modeling, taking the model file, putting that to internal structures, maybe loading that to the memory of GPU if it's available. All that can be run when the model arrives as a red box. And then the actual inference, what is running on a green box. And we want to separate that. And actually we have separated almost everything in the benchmark. So we have huge number of the huge amount of numbers. And we are now desperately trying to make a paper out of that. And that's now essential on this benchmarking. And this whole finding of this is that in this context, we should think about this performance in two phases. Many of these cases that we saw before we started, they try to test that how long does it take to run the machine learning model in Raspberry 3 small model. But they didn't separate these two phases, which is kind of disappointing. And we have two well-known benchmarks called MobileNet and YOLO. And then we have been trying with different machine learning frameworks, TensorFlow, TF-Lite, PyTorch, OpenVINO, TensorRT, and then ONGs. And then running these on several devices, Raspberry 3, Raspberry 4, this Intel NUC device, Jetson Orin, just by using the software, and Jetson Orin with that runtime running the hardware accelerator. And the benchmarks are all the same. And then these are just data about the models. So the other one is having a bigger model, but then using smaller images. And then these are both like image recognition type of cases. Maybe partially because the guys in our upstairs are working on that domain area. So, and then here we have smaller model but bigger pictures, and then wanted to compare these. And just to summarize the devices, so Raspberry 3 and 4, I guess everybody knows them. Intel NUC is this small PC that is typically running Linux. And then this Jetson Orin, which is done like research type of device. Maybe I should have moved that to there, if it better shows what they are. And then these are the benchmarks. So although this is the inference is kind of the interesting part, but we have to think about when the image comes, there's certain pre-processing. It done the inference, i.e. finding whether there is some property that the model has been trained to recognize. and then post-processing. And then this red box is this actually importing all the runtime systems in, loading the model, and then reading the image. This is a bit fall in this picture, but we should have to read the image elsewhere. But anyway, in this drawing, it's here. And then something that we also found out is that for some models, when you start working on them, they seem to need some warm-up time. The first inferences or first 10 inferences are slower until things settle up. We haven't really gone through that, what's happening underneath, but some of these models have that, some of them don't. And then getting to the numbers, and I think the interesting point here is that this red box takes like 7 seconds in Raspberry 4.
But that's more, well, like you said, this is installation.
It's installation, and then the whole green thing is taking less than half seconds after that. And this is something that we
once
realized.
you are prepared to run the model, then you are quick.
Yeah.
But preparing the model for running it, that's slow.
Yeah. And then there's detailed data on inference, and then we can have data on all these runtimes and all these devices, etc. And as I said, so as we speak, hopefully guys back home are working on towards the paper on resulting, summarizing the numbers. And then, of course, one of the things that was interesting to us was this hardware acceleration. And considering and this is these purple or violet boxes here, that considering the hardware, actually it was really surprising long and heavy operation to actually run the green box part, the initialization and loading part there. And maybe it's just related to analyzing to set up the accelerator hardware. And then on the other hand, when we talk about the actual the other parts of the thing, this is, by the way, typo. This should be actually the inference. One of the few slides I tried to fix this morning, and anyway, there you can see that then the hardware accelerator ups means that then the actual inference does not have any, it doesn't even show any more these numbers. So it really gets faster with the hardware accelerator, but at the same time, in this liquid context, the overhead of bringing it in is huge compared to the inferences. And then maybe go to the next topic.
The final thing that we are touching here in the technical sense is that so what? So what will happen if we start putting the AI stuff and all that in the network, so that you can put whatever you like wherever you like? And originally, well, this is kind of like a side thingy in our project. It was mentioned in the project plan that of course we realized that we have to think about the privacy concerns as well. But then when we started to think more and more about what kind of privacy we mean, we kind of run into the Pandora's box, because the regulations and expectation about privacy ethics and so on are all the time growing. And at the same time, if you think in terms of building these rigid IoT networks where you decide that this computer is here and it is running this kind of software, you can work out the privacy things as you build up things. But here, if you can technically create whatever kind of configuration you like, you must somehow take into account the privacy concern. And in order to take it into account, you have to document it. And this is where, when we started to dig down, we really didn't find much previous work on this respect in anywhere in the literature. So the closest things was what do we know about the AI models and the likes, and then we worked a little bit further from there. And again, Pyry will give the nasty details tomorrow, and so will Ali. So looking forward to that. So really, the what we have done is that we have split what we had in this original IoT architecture into zones, and the idea is that the devices are delivering the data, and they are somewhere in the edge and all that.
And the zones should represent kind of trust zones. So meaning that the zone within you have more trust among the parties than compared to outside.
And usually this even works so that today the assumption is that the whole network is trusted, which it definitely need not be, and probably is not in the end. So starting to work out the particular applications, you might have restrictions related to country borders, stuff that is allowed to stay on a third-party server, and stuff that is never supposed to leave the hospital or whatever. And if you have that kind of a data, it means that if you want to process that data, your processing application must go to the location of the data. And this is kind of the motivation why we've been looking so much for the ML models also. And this calls for certain flexibility with respect to the deployment architecture, so that these privacy concerns can be taken into account. And of course, such need does not emerge until you have these isomorphic modules that can go anywhere. So this is well, even though this was not planned in the project plan, I think that this was major discoveries, among the major discoveries in the project. So what we at the moment have is a running prototype where certain things have been added to protect the privacy. Big thing is that once you create whatever artifact you do, you analyze it and create a data card out of it, which is put to the data repository. And that card represents that particular module, data source, whatever, and it defines conditions which restrict where it can go in the deployment architecture. All right, when doing the allocation of different computations, these definitions that are given in the cards and requirements of the domain, you pick up the trusted zones, or you define the trusted zones in the architecture. And then following the zones, you decide which of the components can go where. Are they allowed to leave Switzerland and all that. And then again, with the once deployed, this is taken into account, and even during the execution at runtime, it is possible to monitor that the models are running in a place where they are allowed to run. So it is a bit like adding, in addition to the technical runtime architecture, you add a legal architecture or what would be a good name for it? I'm not sure yet. Something that comes from the regulatory and other restrictions that we probably don't have a very good language even at the moment used to express all the restrictions and all the relations and all that stuff. Or do we, Ali, have it today?
For tomorrow morning, you're ready.
Maybe tomorrow. Yeah. And well, we have a prototype running, so that means that we have also the prototypes of these different types of cards available, describing all the metadata that you would need to this. So as a starting point, we use ODRL. Do you remember where that come from? Ali, what is ODRL? Yeah.
It is the right flag.
Yeah. And well, for the machine learning model, you define constraints that you must take into account. What is the risk level you are accepting for input and output, and then same thing for the different zones that define whatever restrictions there are for that particular zone, again in terms of risk. We really need a better way to explain this, but that would call for I don't know, something graphical that would make things easier to explain.
But it's anyway also one of the things we're currently working on, and then Olli will talk more about that. That is core of these PhD thesis. So tomorrow.
All right. The things that we are eager to work on together with you, or if none of you is interested, then we are going to do that by ourselves, is the help integrate WASM with existing stuff. So I don't know, API generators, whatever that would help in doing the bindings to these machine learning models, and whatever stuff you find outside of WebAssembly that would be helpful. So in some of our implementations, what we have done is that we have been using Python as the glue code between WASM and whatever libraries you can think of written in Python. And this is, of course, horrible because Python brings in so much memory usage and so much slowness and also security holes and so on. But in order to demonstrate things, that's what we did. Building bigger installations, that's one of the things, which is the reason why I went to up north in Finland earlier this week to talk about the really big deployments for demonstrating and prototyping things. These privacy and security things that we just touched, that's a really novel thing that I think that if we would have had a company guys in our project, they would have wanted to patent something there, but we were stupid and put it into research paper. And finally, building demonstrators for working and shuffling around AI-related stuff, be it real network or be it something where devices are virtual and all that. That's also something that would be cool. Possibly combining that with the deployment in the large and testing, I don't know, this building a digital twin of a complex IoT network on a computer with the virtual machines and the likes. And this is it. Thank you.